and now we're going to hand over to the Poen session with a set of 4 interesting papers I'm super excited about. As a very first speaker, Ateeq is going to start us off with an in-memory embedding of CPython for offensive use. Ateeq, are you here? Cool. Can you try sharing your screen again so that we can see your slides?
Let's try it.
Yeah, fingers crossed.
There you go.
Awesome. We see your we see the full. Okay, now we see the slides. Perfect. So please take it away. The floor is yours.
Okay.
Thank you.
Okay. Thanks for joining me. So basically, this was some research done by Chapman and Chris. We all work for a company called SCYTHE. We'll first cover why we ended up doing this research, what our actual contributions are, and the results in summary. So basically, if you consider large companies, security research is usually divided into two categories. You'll actually have folks who are in what is called the blue team and folks who are in the red team. And the purpose of the blue team is essentially to prevent attacks, like from the defense side, whereas folks in the red teams are actually more interested in exploiting the systems or software that's enterprise and actually getting in, and basically sharing their findings with the blue team, thereby preventing future attacks. Red teams and blue teams, although they're engineers, most of them are actually not programmers per se, although they will find scripts that are published by security researchers and basically apply those for their work. And I would say quite a few of those existing security researchers ends up being scripts written in Python. Because they're not programmers, they're not going to be very interested in writing exploits in C or C++, if that makes sense. They're not really interested in native exploits. But if somebody has something already written, they want to apply those to basically quickly identify issues in their enterprise systems. So yeah, as I mentioned, Python being a very popular language, there's a ton of scripts that are written in Python. If a security researcher wanted to use one of those scripts in a device on their enterprise, let's say they somehow use an exploit to land on that device, what they would have to do would be to transmit an embedding of Python. And usually what that means is basically copying all the files related to the interpreter, as well as all the packages necessary, and then execute that. But the problem with doing it that way is that most of the enterprises will have security sensors, and if a device that's not authorized to have Python has Python on a disk, it's immediately going to get flagged. So it's not really a viable attack vector, if that makes sense. So our contribution is basically an embedding of Python that runs entirely in memory. So what we mean is, let's say you have a 0-day or end day and you could compromise the process. You can actually load this Python interpreter in memory without ever touching disk. You can actually load all the packages also in memory and run all of those things. And the benefit being, most of the security sensors looking for things on disk will actually not look for this CPython that's actually running in memory. Although there are some security sensors that do memory scanning, they're not really targeting CPython, and they're actually not that sophisticated, specifically because scanning memory is very expensive as an operation. So if you've ever downloaded Python, one thing you're going to notice is that it's actually a very small. And I'm only talking about Windows flavor, but the other versions are also more or less similar. But basically, it's a very small exe, and what this does is it actually loads everything from something called a shared library or DLL. In our case, we used Python 3.8.2, although this applies to other versions. But yeah, you're going to come across a Python 3.8.2 DLL on disk. So what our contribution was, hey, can we generate a Python 3.8.2 DLL which runs entirely in memory? That was the first case. And second case was all the packages that come stock with a Python implementation. Can we actually also load those from disk as well? And that's where we produced something called a custom zip loader derived from the zip importer that actually exists in CPython, which can actually load packages in zip archives directly from memory. And also special cases, specifically C extensions or PYD files in Windows, which are actually written in C, but can be imported from Python. So when it comes to the shared library, there's existing research, and this goes back all the way to 2004, how you can actually load a DLL directly from memory versus from disk. So like the standard loader from Windows or Linux or Mac OS provide something like DLOpen, or in the case of Windows, it's load library. And what these do is they have an expectation that the file for the shared library or DLL is actually on disk, and then it basically loads the library into memory from this file, and basically does all the fix-ups and everything like that. The research from 2004, and there are quite a few open source code out there which implement that research, where just from a simple memory buffer, you can actually load a DLL, for example, just from memory without it ever touching disk or being on disk. But simply trying to do that for the CPython DLL is not going to work. And the specific reason being that there are certain packages it's expecting to locate, for example, encodings, codecs, ABC, and so forth. And because it's not going to find these, simply calling load library from memory and then trying to do PyInitialize is not going to work. So the two things we had to do, the first case is basically we want to initialize an isolated configuration structure. And the reason we want to do that is, let's say the device already has an world. If we don't use an isolated config, what's going to happen is it's going to look at as we call PyInitialize, it's going to look at the environment variables and see, hey, there are some packages in some other folder on this device, when it might not even be the right version of Python. So just to prevent things like that, we actually do we actually initialize Python with an isolated configuration. And the second part is because we don't want to touch disk whatsoever, we want to provide our own mechanism to load these packages, encoding, coding, ABC, all of these from memory. So looking for those on a device actually does not make sense either. So to load these packages, one of the things we did, as I mentioned, was we derived zip import, and we actually created something called CBA zip import, and basically for initials, our first names, and it's CBA versus ABC because ABC in Python actually stands for abstract base class. So we had to come up with a different. And this zip import does is, instead of finding the zip archive in a file or from a zip archive in file, what this can do is actually just load those packages directly from memory. What we do is we actually freeze this module and basically add this to the PyImport frozen modules table. And the benefit of doing this is basically when PyInitialize is called, it's actually going to go through this table and all the modules that are in this frozen table. So basically this CBA zip import gets loaded. There's an additional change that needs to be done, and that's basically a change in the Py lifecycle C file. And basically what that does is basically adds the CBA zip import as the third loader in the meta path. So what that means is, when you're trying to load encodings, like import encodings, first it's going to look, this request is going to go to built-in importer. If that can't find it, then it's going to go to the frozen importer. If that can't find it, then it's going to go to the third item, which is the CBA zip import. And CBA zip import basically has the offsets to both the to all the packages that come with a stock implementation of Python. The last thing that this CBA zip import can do is it can actually load C extensions also in zip archives, because as we mentioned that we don't want for any files on disk, or we don't want to load anything from disk. So when it came to the stock packages or the stock modules that come with Python, there's quite a few of them. For example, hashlib and things like that. So what we want to do is basically we generate a zip archive for all of these and put it in the zip file. And then, similar to XSD, basically what we do is we generate a C source file out of this. And during the Py lifecycle call to CBA zip import, it basically adds the address of this zip archive in memory. And the benefit of this being like, okay, now when somebody calls import encoding, or when doing Py initialize, it calls import encoding, it knows exactly where to find it in this zip archive, and it's loaded by the zip importer. The C extensions, as I mentioned, and this slide is only for Win64, but the same case applies to x86 as well as other platforms. Basically, the PYD files, the default implementation or the stock implementation, are compiled in a way that some of them are relying on DLLs to be on disk. For example, the SSL or underbar SSL module expects the OpenSSL DLLs to be on disk. So those actually need to be recompiled such that they're statically linked to all of those shared libraries, such that they're now looking for on disk. And excuse me, exactly the same thing happens for those where during the Py lifecycle import event, basically we add this list of PYD files in there. There were some changes when it comes to point E. Basically, this is referring to a change we did in the derivation of our zip importer, where we added code to allow importing these C extensions from the zip archive. What this means is basically when it comes across a PYD file in a zip archive, it actually calls another function we wrote, create direct in memory in the shared library, and basically provides that the data to this create dynamic in memory, which is basically an implementation of load library from memory. So there are a couple of special cases. So there are quite a few modules that are actually going to use C types, and specifically C types.python API, which actually is a reference to the core shared library. Excuse me. For that to work, what needed to happen is basically there's a call to get module handle. So anytime it's looking for the get module handle for the shared library, we actually need to provide it the location where we actually loaded with our load library in memory versus not making that change. What would happen is the call would, and because it was not loaded by the Windows system loader, it's going to actually get module handle. It's actually going to give you an offset that's incorrect. It's going to give you the offset of the process itself versus the shared library. So that's why we need to make a change there. And one of the caveats is, of course, when you're calling any Python code from C, you actually have to do pygl state ensure, and then run your Python code. And then once done, you have to do pygl state release. If for non-stock packages, if you have additional PYD files that you want to actually load using the shared library, again, the same thing applies as case one, where if your code actually calls get module handle ex, you have to use the sysdll handle instead, because as I mentioned, these two function calls excuse me, will not have the proper will actually the location of this shared library, because it was not the Windows loader that ended up loading it. And the last special case to remember is it has the same requirement as a standard C. There's an expectation that the default version of the C runtime needs to exist on the device on which you are going to deploy this CPython. So the demonstrations are available in the appendix. Variations of this have been in use for a year in production by our customers. And basically, the source code is available for anyone who wants to try it out, as well as any of the artifacts if you guys want to try it out. And now, if you guys have any questions.
Awesome. Thanks a lot for the presentation. Questions, folks? We still have a minute or two. I'll kick it off with one. Did you integrate it into some other frameworks that allow easier deployability? So think about maybe MeterBreeder or something else to push it into other target systems and deploy.
Yes, I mean, it's entirely possible if you want to do something like that. Because everything is encapsulated in a single DLL, the only thing you would have to do is basically transmit this over. So it wasn't as shell code. Yes, you can do that. Yes.
Which would lead to my next question, right? What's the overhead? Are we transferring 5, 10, 100, 200 megabytes? What's the sweet spot here?
Oh, I think it's actually under 20 megs. So basically, one of the demonstrations in the artifact, the first one, what it does is it loads it in notepad.exe, and basically, if you look at it through task manager, you're going to see this thing, and it's roughly like a 20 meg. Because so if you look at the shared library, excuse me, if you look at the shared library for a stock implementation, it's roughly 4 megs. Because this shared library actually has all the packages that a stock CPython would have, all of it archived. I think we did maximum compression. It doesn't really matter. So basically, all of that being transmitted is roughly 20 megs.
Right. That's actually not bad. And this kind of enables you to make all the processes somewhat scriptable. Right, so you can add script extensions to anything you like, which is kind of cool extension that goes beyond the hacking aspect of it.
Correct. So I mean, if you wanted to, it's a nice embedding. Yes.
Yeah. One of the questions, there's 2 questions in the chat. One by James, which was pretty much the size question that I just asked. The other one by Will Pierce. How do you load it into memory? RDI, SRDI from .NET. What agent do you use to load it?
I think it's entirely up to you. It's entirely up to you how you want to load it. If you look at the artifacts, the way we do it is, in the case of Notepad, where we're emulating, is just like a create remote thread, and then write process memory, and then write process memory, create remote thread, and then you're good to go.
Yep. Okay. Cool. Thanks for the talk again. If there's more questions, you'll stick around and answer them. Use the chat, and you can follow up and go back and forth. Cool. Thank you.